Hello, my name is Michael Dombach. I am Senior Vice President of HyperWorks Program Management, and today I will be reintroducing you to HyperWorks. Altair has quite a long history in post-processing, dating back 3 decades, and HyperWorks has been at the center of it all. This video highlights the look and feel of our user interface dating back all the way to the MS-DOS days. So what do we mean this time by reintroducing HyperWorks? We feel that this version is a revolutionary part of the evolution of our interface. A modern, easy-to-use, intuitive, and discoverable user interface with the same executable, the same hypermesh database, and the same scripting APIs. So you could think of it as a different window into the HyperWorks interface. For veteran users that have been using HyperWorks for possibly decades, will be able to pick up the new user interface at their own pace and own learning curve because the same executable will be launchable from either. So migrating HyperWorks to our new user interface brings the power tools available in HyperWorks down to an easier learning curve. Our end goal of moving to the new user interface is to not simply reduce the learning curve, but also to make sure that we have a congruent look and feel to all the products under the Altair umbrella. This facilitates our user switching not only back and forth between HyperMesh, SimLab, and Inspire, but beyond modeling and visualization tools, so our users can leverage all there is to offer under our unit licensing system. So rather than walk you through the over 1,000 PowerPoint slides that I would like to talk about, we decided to put together 20 minutes of videos to showcase HyperWorks with an end-to-end workflow from model assembly all the way through to documentation and final optimization. We'll start with model assembly. So first, we'll import the BOM file. The BOM file may or may not come from your PDM system or contain PDM information. If it does, that does automate some level of organization. So first, let's load the 5mm representation for the part sets associated with our load paths. The next thing we'll do is we'll load a Corsair 10mm representation for the rest of the vehicle. Now, we're going to skip loaded here because we already have a 5mm mesh representation loaded for those associated with our load path set. So now we have a 150% BOM of our body in white. So let's say we want to take a look at the shock tower and replace it with a casting. So let's walk through how we might create a mesh manually using our new direct mid-meshing tools. So the first step is to generate the initial mid-mesh. So we'll submit the geometry to mid-meshing to generate that starting point. From here, these tools operate on the mesh representation of the midplane, not a geometric one. So editing faces, filling in faces, or removing features from geometry onto the underlying mesh will now dictate how the batch mesher handles them when we perform a rebuild in the end. So we're able to create new edges by nodes or derive them from the geometry. We are able to imprint features from lines from the solid to get additional detail, or we can suppress features, feature lines where the detail is no longer required. We're able to align edges and faces according to the geometric topology as needed. For example, when the automatic process fails to represent a perfect circle here. And from the clean topology mesh representation, the last step will be using the mesh rebuild process, which will use the batch mesh criteria, in this case 5mm, to remesh the part, submitting the topology result as input. Finally, mapping the thickness is a feature that has been in HyperMesh for quite some time, but is mostly ignored. Now, in our new user interface, it is discoverable and at the end of the ribbon as the last step in the workflow. Now that we have this new part meshed, we'll bring it back into the body in white. So let's now organize our BOM using the attributes provided to us from the CAD system. From here, we can see that we have flags for a fixed roof, panel roof, left-hand drive, and right-hand drive. The part sets for these have been automatically created from the PDM flags. The only step left is to drag and drop these part sets into 4 different vehicle configurations. So here we drag the left-hand dash, the panel roof for one configuration, and then repeat the same process for the other 3 configurations. So when we are done, we'll be able to toggle on and off each of the modular assembly representations. It should be noted that if you do not specifically select part representations to belong to a configuration, they belong to the common model, so they will be associated with all vehicle configurations. So this is only necessary for those that belong to a unique configuration. So here we are toggling the active vehicle configuration between the 4 configurations: left-hand drive, right-hand drive, fixed, and panel roof. So the next step in our process is to realize connections, which also may have different representations. So here we're going to load connections from our connector library. And here are the connectors for the body in white. We can realize connections right from the idle state. In this case, we'll realize spot welds and adhesives. Here you can review the type of connections that have been realized. Note that we create parts for all of the connectors so that they can be easily assigned to a part and then moved to a subsystem. So finally, we create a subsystem for our body in white and save the subsystem to the subsystem library. And again, when we save these into the subsystem library, that also facilitates a collaboration with other teams that may be sharing the same library. So we now have 4 different vehicle configurations for a body in white and saved as a crash representation. So the next step would be move to the subsystem browser. So our subsystem workflow is analogous to our part browser workflow. So we will ensure we keep track of all the entities that belong to the existing subsystem, but also we want to maintain the subsystems from existing include files. So we'll load the remaining include files from an existing HyperMesh binary. We allow dragging and dropping of any entity from any view in the model browser, in this case into the subsystem browser. So we have includes created, or excuse me, we have subsystems created from each of the individual includes, and then we can make sure that we save these all as a subsystem representation for our crash model. We also support subsystem color mode now, which enables an easy visualization of all the entities within each subsystem. We also allow multiple representations of subsystems, either from the same solver or any number of our supported solvers. So the next step is to generate separate load case configurations with the subsystem browser. From here, you can now associate each one of these includes to its own subsystem configuration via subsystem sets, which are analogous to the part browser's part sets. So we've organized all of our includes associated with an offset barrier left-hand side, a right-hand side, and a side impact. So here the subsystem sets contain only those includes that represent each of these load cases. And any subsystem that is not explicitly called out with a subsystem set, analogous to the part browser, is associated to a common subsystem, which means it belongs to all of the load cases. So for any active load case configuration now, we can now export a complete set of input decks for any one of these load steps, writing out each of the subsystems simply by activating its load case. Now that we've defined our load case configurations, a key feature to leveraging the subsystem representations are the subsystem attachments, which is new for 2020, supporting bolted connection types. Here we'll realize bolted joints between our body in white and the door subsystem. We can realize these bolts many different ways. Here we choose a configuration of the attachments to be rigid patches. Our rigid patch realizations for bolts support OptiStruct, Radios, and Dyna. Our new attachment controls are also solver agnostic, so this removes one of the largest bottlenecks in the model assembly process. Our holes can be selected or auto-detected. In this case, fill hole is used, and the rigid patches are automatically generated between the 2 subsystems. Also note that when the rigid patches are realized, they're automatically organized into their appropriate subsystem, which is made clear by our new subsystem color mode. Next, we would like to generate a new subsystem to place these attachments so they can be added to our vehicle configuration and then realized and unrealized as we change our vehicle configurations. Here we're reviewing the rigid patches with the same visualization tools we use for contact pairs on the rigid body merge part. Finally, we'll realize the rest of the connectors for the other subsystems that we loaded into the model. Everything outside of the body in white has been realized now, and the user can export a set of solver decks for any one of these vehicle configurations in all of our defined load step configurations. And then lastly, any and all of the comments are maintained as metadata in the subsystems. So your solver decks can be reused later with the same information. Next, we have a short video showing off our new morphing and mesh rebuild tools with the new user interface. So the first step is to bring this bracket in and roughly position the part using the Inspire-like move tools. The second step is to use free morphing to do a finer adjustment to morph the bracket itself so that it conforms to our rail. So the power of hypermorph has been here for years, but in this particular version, we have made the learning curve much more shallow. There are no longer any handles or domains to work with. Everything happens behind the scenes. Here the user is specifying a gap of the flanges to be away from the rail flanges. Another new feature is our replicate function, which we can use to copy certain areas of our mesh from one area to another, or multiple copies of it. In this case, the user specifies with the Inspire Move tool the direction and the number of repetitions that they would like to copy this particular feature in the rail, which will then be imprinted on the original mesh. The user simply selects the number of instances and the Move tool picks a direction. This can also be used to replicate about an angle, rotating about a plane. And then finally, we want to perform a mesh rebuild operation to clean up the rail part after we've imprinted these new features. So the mesh rebuild will utilize the batch mesher criteria, taking the old mesh again as input. What if we want to redesign a part or a part assembly completely from scratch? What if our manufacturing process had changed? For example, we're able to go from stamping to a 3D printed part. In this next set of videos, we'll take this assembly of stamped sheet metal parts and walk through a conceptual optimization process from beginning to end. The first step of the process is to define our design space. So we'll first isolate the subsystem of interest and then fill the gaps and holes to complete a volume for the assembly. Then we'll fill the design space with voxels. In this case, we'll fill it with 5mm voxels. And then we will perform a Boolean on the voxel mesh between our designable parts and our non-designable parts. So here we select the design space, and then also in the exclusion set, the non-design space. From the resulting Boolean of voxels, we can then submit to topology optimization, and then when we're finished, we have a ready for interpretation 3D printed variant of the subassembly. We also decided to highlight some key crash workflows that are now available in an intuitive, easy to use interface. And some of these were directly targeted as some key bottlenecks. So let's start with the new seatbelt routing tool, which will create an entire seatbelt assembly all at once. By directly operating on the model, we can quickly and easily select the proper components to create an industry standard 3-point belt assembly with an anchor, a slip ring, and buckle attachment points. We simply identify the components that we would like the belts to wrap around, and the seatbelt is routed automatically. And we repeat this process for the lap belt. When we're done, interactive editing of the belt is also supported, again using the model as a menu paradigm. Once we're satisfied with that, the tool allows for the automatic creation of our slip rings, pulleys, retractors, and pretensioners by simply identifying them in the browser. In this next video, we'll walk through our seat mechanism tool. This is a generic tool that can be used for any kinematic system, but in this case, we're showcasing it for safety preprocessing to adjust our seat assembly to several predefined positions. The mechanisms can be easily absorbed from existing FEA models as well. Other bonding additions, such as the dummy's hand or the feet-up pedals, are also honored. Notice also that after positioning, the belt does not require any rerouting. The last crash workflow that we would like to showcase is our new Pedestrian impact tool. For this workflow, we want to automate the setup of all of our marking and positioning parameters, which are also happen to be customizable. The tool supports all relevant pedestrian market regulations. To ensure correctness, we provide the ability to validate all marked entities, construction lines, impact points, and flexible tape. This facilitates precision and repeatability in generating our test zones with physical test markings. In this workflow, we can preview any of our final position impactors and export them all to error-free solver decks. So here we'll preview two different head impact locations, one lower leg, and finally one upper leg impact location. Now that we've finished running our crash model, the next step is to showcase some performance enhancements in our post-processing. We call it upfront data loading. So HyperView is now able to select only the time steps that the user is interested in loading, and then utilizes multiple processors to ensure we have dramatically improved load times. During this process, we also ensure that HyperView remains completely interactive during the entire process. Once the results are loaded, they can then be cached into memory to give the user high performance reactivity during the course of their post-processing. Finally, we're ready to generate some reports. Automated reporting is now part of our core solution. So engineers can now predefine report layouts using Microsoft Word or PowerPoint. These can be your own or from your employer's corporate template. The modules are used to easily automate the content creation. All the images from all the pages in HyperView are then captured and exported to the report template, and we're able to save and reuse this template in a library of standard templates. This ensures that all your reports have a consistent look and feel from report to report. The entire process can also be run in batch mode, enabling the report generation to occur on your HPC cluster as part of the job submission process. So we'll just cycle through and make sure everything is finished. And when it is, we can then export the session using either Word or PowerPoint format with the core templates or your own corporate template for automatic report generation. And then when we're finished here, we'll preview the PowerPoint report for the crash workflow. Once we've finished analysis and reporting, of course, we would like to make recommendations for improving our design. So for fine-tuning design, we have implemented a fast, easy-to-use size and shape workflow that can perform a design of experiments or optimization using HyperStudy engine in the background. Again, the paradigm here is the model is the menu. No longer are we expecting users to perform a parsing of ASCII files or result files. The user is directly able to select parts off of the model and easily create design variables for gauge and even for shape using HyperMorph. You can also preview any of these variables directly from the interface. So here we'll preview two gauge variables for the rail, inner and outer, and also a shape variable for the height of the rail. So again, the model is the menu, and being able to easily see what you're submitting to HyperStudy. The next part is generating the responses. So we'll turn on the whole body in white, and then we'll create a response for our mass using everything that's on the screen. For our displacement response, we simply need to pick off of the model. There are no node IDs, there's no nominal run, there's no combing through results files. We simply pick the node and select the displacement to measure the torsional stiffness on the body. We'll then submit the DOE, which in this case takes about 1.5 hours on this laptop. And once the design of experiments is completed, we can review all the results directly onto the model without opening any other client or any other user interface. So here the user picks a run out of the DOE and directly places a contour plot on the model. More importantly, we can do a sensitivity study. So from these design variables in the DOE, we can sort the sensitivity of each of the design variables with respect to this torsional displacement response and contour those directly on the model, something that you can't do with a tabular entry. You can also view a scatter plot of any of the design variables or any of the responses with respect to anything else directly within HyperWorks. And then the last part before we move to optimization is we can do a quick trade-off study, varying the inputs in the DOE from minimum to maximum to see how they might input our response. So once we've done that, we know what design variables are going to be impacting our optimization the most, so we can go to optimization. So we'll set up an optimization study and create an objective function. In this case, we will minimize the mass, which is essentially the mass of the entire body in white. And while we're doing that, we'll constrain the torsional displacement of the body. So in other words, we'll make sure that the torsional stiffness does not get any less than the initial design while minimizing the mass. So that is all there is to it to get an optimization run set up from the DOE. Once the optimization is completed, we can review every single one of the solver runs and easily determine which designs are feasible or infeasible and plot any of them by plotting them directly onto the model. So here's a review. Similar to the HyperStudy tabular entry, they're color-coded by what is feasible and active, inactive constraints and what is the optimum design. So here we'll load the optimum design and review the torsional displacement. Again, we're doing this without ever leaving the HyperWorks client or launching another client. We can also review any of the optimization iteration history from the objective function, minimizing the mass, to the displacement constraints, and all of the optimal gauge variables that are in the final design. So basically, the HyperStudy functionality has been completely embedded within HyperWorks for any user level to leverage the power of optimization at any point in their design. So I hope you enjoyed a walkthrough of a complete set of workflows available in HyperWorks 2020. Please remember that we have over 1,000 slides of content that's available in this release, and these are just some of the key highlights. So if you have any questions, please be sure to ask your Altair contact. And also please be sure to be on the lookout for more workflow videos on YouTube. At the end here, I would like to acknowledge our entire HyperWorks development team that has been working very hard to get you as much content in this release as possible. I also have a special call out to our framework team and QA team that have gone above and beyond for this particular release. So thank you very much to those teams as well. Finally, please visit our high fidelity modeling demo booth for more detailed product demos, access to training material, and live interactions with several of our product experts. Thank you very much and enjoy the rest of the conference.